Welcome back to QHSE Talks.
Thanks for having me back. We've got a lot to cover today.
We really do. I want to start by having you, the listener, imagine a scenario. You are standing on the floor of a massive high-capacity chemical manufacturing plant.
Okay, setting the scene. I like it.
Yeah, so right above you, there's a pressurized line, right?
Yep.
And it's carrying corrosive sodium hydroxide. And it develops this microscopic fracture.
Well, it was basically a nightmare scenario for any safety professional.
Exactly. And within milliseconds, that fracture propagates, the pipe totally fails, and a high-velocity spray of this caustic liquid erupts right downward.
And at that point, all your engineering controls, like your pressure relief valves, your primary containment, they've all completely failed.
Right. They are gone. In that exact fraction of a second, the only thing standing between a worker and just, life-altering chemical burns is a barrier of synthetic polymer that's maybe 2 millimeters thick.
And the scary part is that 2-millimeter barrier has to perform flawlessly. I mean, it has to resist chemical degradation on contact. It needs the tensile strength to withstand the actual kinetic impact of the spray. And, well, maybe most critically, it has to be worn perfectly by the worker in the first place.
Right, because if they didn't zip it up right.
Exactly. There is literally zero margin for error when you reach that specific point in the safety chain.
And that terrifying lack of margin is our entire focus for this QHSE Talks today. We are zeroing in intensely on a critical core competency for safety professionals, which is ASP 11, Domain 2, Topic 8, Part K.
Which covers the safety fundamentals of personal protective equipment, or PPE.
Right. And let me lay out the stakes for you, the listener, really clearly here. Whether you're actively preparing for your associate safety professional credential or you're a practicing safety manager walking the floor right now, mastering this domain is non-negotiable.
It really is. It's not just about passing a test.
No, not at all. It dictates how you conduct worksite assessments, how you evaluate residual risk, and ultimately how you keep people alive when, like we said, those primary defenses fail.
Because it goes so much further than simply handing someone a pair of safety glasses and telling them to be careful.
Yeah, way further. We've got a whole stack of sources guiding this QHSE Talks today, right? We're pulling from CSP exam study guides, OSHA 1910 general industry standards, safety engineering handbooks, the works.
And we are unpacking a highly complex regulatory-driven management system here. I mean, we have to understand the thermodynamic properties of materials, physiological limits of the human body, the physics of hazard energy. It's a lot.
It's like decoding a massive puzzle. And I want to start by challenging a really common misconception right out of the gate.
Let's hear it.
Well, when you ask the general public to picture workplace safety, what do they see? They almost always picture a person in a bright yellow hard hat, right? With safety goggles and a high visibility vest.
Oh, absolutely. PPE is basically the universal, recognizable symbol of safety.
Right. But when we look at the foundational architecture of our field, and I'm talking specifically about the framework established by the American National Standards Institute in ANSI Z590.3, which Elisha also adopted, PPE is actually categorized as the absolute least effective means of controlling occupational hazards.
Which is always such a massive paradigm shift for anyone entering this profession.
Right. It sits at the very bottom rung of the hierarchy of controls.
We literally spend billions of dollars globally on protective gear every year. Yet our foundational philosophy dictates that we should do everything in our power to avoid ever having to use it.
We want to eliminate the hazard entirely first, right?
Exactly. If you can't eliminate it, you try to substitute it for something less dangerous, say a less toxic chemical.
And if substitution fails?
Then you isolate the workers using engineering controls, so like physical machine guards or industrial ventilation systems.
Okay, and then administrative controls.
Right. That's altering how the work is actually performed, like rotating shifts to limit exposure. And then finally, PPE is that last desperate layer of defense.
I always think of it like the goalie in a soccer match.
Oh, I like that analogy.
Yeah, think about it. If the hazard, which is the opposing team, makes it all the way to your goalie, the rest of your defense has completely collapsed.
Right. Your engineering controls missed the tackle.
Exactly. Your administrative controls were just totally out of position. And sure, we celebrate the goalie when they make a spectacular save, right? We love the hard hat that took the hit. But as safety professionals, we really want the ball stopped at midfield.
We want our goalie to be the most bored person on the entire field.
Yes. Bored goalies mean a safe work site.
I'll actually take that analogy a step further, because unlike a human goalie who can anticipate a shot and dive across the net. PPE is entirely passive.
Right, it doesn't react.
It cannot adapt at all. If we look at the underlying physics and, honestly, the occupational psychology of why it sits at the bottom of the hierarchy, it really boils down to two critical vulnerabilities.
Okay, what's the first one?
First, PPE does not diminish the hazard's energy or toxicity in the environment.
It just blocks it from the person.
Right. The toxic vapor, the falling steel beam, the deafening noise, that hazard remains physically present in the workspace. It's operating at full capacity mere millimeters from the worker's skin or respiratory tract.
So the danger hasn't been neutralized at all. It's just being temporarily held at bay by a piece of plastic or rubber.
Exactly. And the second vulnerability is its absolute dependence on continuous, perfect human compliance.
Oh, yeah. Humans are messy.
Extremely. I mean, a ventilation system works regardless of the worker's mood, right, or their comfort level, but PPE is a procedure.
The worker actually has to actively put it on.
They must actively don the equipment correctly, ensure an airtight or secure fit, and then wear it for the entire duration of the exposure without a single lapse.
And maintain its physical integrity over time, too.
Yes. If a worker loosens their respirator for even 5 seconds because, I don't know, their face is itching, the protection factor instantly plummets to 0.
That's terrifying. So, given these massive inherent flaws, when is it actually acceptable to deploy PPE? I mean, why do we use it at all?
Well, according to the standards, we deploy it in 4 specific scenarios.
Okay, lay them out for me.
First, we use it as a temporary measure while we are actively engineering a more permanent, higher-level control.
So like a stopgap measure.
Exactly. Second, we use it when engineering or administrative controls are technically or economically unfeasible. You just physically or financially cannot build a better system.
Makes sense. And the third?
Third is when safe work practices alone simply cannot bridge the gap to a safe exposure level. You've done everything else, but the risk is still too high.
And the fourth scenario?
Emergencies. Chemical spills, uncontrolled releases, situations where all the other normal operating systems have broken down.
All right, so that sets up our operational philosophy perfectly. We really don't want to use it, but when we have to, it has to be deployed with absolute precision.
Precision is the key word.
Right. So how do we determine what specific type of goalie we need for a given threat? Because you can't put a hockey goalie in a soccer net and expect them to stop the ball.
No, they'd be wearing the wrong gear entirely.
Exactly. Which brings us to the bedrock of this entire protective system, the formal hazard assessment. And this is heavily governed by OSHA 29 CFR 1910.132, right?
Yes, this is where we transition from safety philosophy into strict legal mandates. Standard 1910.132 contains a non-negotiable directive for employers.
And what's the core of that directive?
The employer must actively and systematically assess the workplace to determine if hazards are present, or are likely to be present, that necessitate the use of personal protective equipment.
Let me pause you there, because the phrasing "must actively assess" feels crucial, especially for anyone studying for the ASP exam.
It is paramount. It is not a passive recommendation.
Right, so a safety manager can't just sit in an office, wait for a worker to get a metal shaving in their eye, and then say, oh, I guess we need goggles on milling machine number 3.
No, absolutely not. You have to anticipate the failure before it happens. You are essentially functioning as an occupational investigator.
I love that framing. Occupational investigator. What are we investigating?
Well, you're categorizing your findings into 2 distinct buckets. First, you are hunting for physical hazards.
Okay, physical hazards like what?
This requires calculating kinetic and thermal energy. You're looking for moving machinery that could strike a worker, extreme temperature fluctuations that cause thermal stress.
What about light? Like from welding?
Yes, high-intensity optical radiation is a major physical hazard. Also, rolling or pinching objects that create crush hazards, electrical voltages, and sharp edges.
Got it. So that's the physical bucket. And the second bucket covers health hazards, right?
Yay!
Which honestly feel more insidious to me because they might not cause immediate trauma.
They are insidious. Health hazards often lead to chronic, fatal conditions over decades, rather than an immediate broken bone.
What exactly are we looking for in that bucket?
You're evaluating the potential for overexposures to harmful dusts, like respirable crystalline silica, chemical vapors, ionizing and non-ionizing radiation, and biological agents.
And once you identify all these hazards, both physical and health, the regulatory obligation escalates significantly, right? You don't just order gear from an industrial catalog and hand it out in the break room.
No, not even close. You must establish a formal, written comprehensive PPE program.
Which involves a lot more than a one-page memo pinned to a bulletin board, I assume.
A lot more. The mandated program actually requires 9 highly specific elements.
9. Okay, let's walk through the heavy hitters.
Well, you have to document the selection criteria based directly on those identified site hazards. You must clearly define both the intended use and the strict limitations of the equipment.
Limitations are huge.
And you have to factor in the work mission duration.
Wait, let's explore that duration variable for a second. Because if I'm selecting chemical gloves, why does it matter if a task takes 10 minutes versus 4 hours? A chemical-resistant glove is chemical-resistant, isn't it?
See, that assumption right there is actually a fatal trap for many young safety professionals.
Really? Why?
Because chemical resistance is not a permanent state. It is a time-bound mathematical curve. We have to look at 2 specific phenomena here: penetration and permeation.
Okay, break those down for me. What's penetration?
Penetration is macro. It's when a chemical slips through a physical imperfection in the glove, like a pinhole tear or a degraded seam or a zipper.
So a physical hole.
In permeation.
Permeation is a molecular process.
Mm-hmm.
The chemical actually dissolves into the glove material itself, diffuses through the polymer matrix, and then desorbs on the inside against the worker's skin.
Oh, wow. So the glove looks completely intact on the outside, no holes, no tears.
Exactly. It looks fine, but the chemical is literally migrating straight through the solid material at a microscopic level. That is precisely the danger. Every single chemical glove combination has a specific breakthrough time.
Give me an example of that.
Okay, say a nitrile glove might offer a breakthrough time of 120 minutes against a specific industrial solvent.
So if your work mission duration is only 10 minutes, you are perfectly safe.
Right, but if your work mission duration is a 4-hour shift and you don't mandate glove changes,
that solvent will permeate the barrier, and worse, it'll be trapped inside the glove against the worker's skin, which actually accelerates absorption.
you absolutely must tailor the gear to the clock.
That perfectly illustrates why the written program has to be so exhaustive. It also has to cover decontamination procedures, disposal protocols, rigorous training mechanisms, and a formalized periodic evaluation to ensure the program is actually working.
It's a massive undertaking. But I want to zero in on a concept from the sources that I know always generates friction on the job site: employer liability and employee-owned gear.
Oh, yeah. That's always a debate on the floor.
Right. So the regulations make it clear that the employer must provide the appropriate PPE, usually at no cost to the workforce. But let's say I have a veteran machinist. He's been cutting steel for 20 years. He hates the company-issued safety glasses, so he brings in his own expensive tinted glasses from home.
It happens all the time.
If the employer isn't paying for them, why is the employer still legally on the hook for them?
Because the Occupational Safety and Health Act places the ultimate responsibility for a safe workplace squarely on the shoulders of the employer, not the employee.
So you can't just wave a waiver and say, his glasses, his problem.
You absolutely cannot outsource your regulatory liability. If you allow that machinist to wear his personal glasses, you, as the safety professional representing the company, must verify that those specific glasses meet the rigorous ANSI Z 87.1 impact standards.
You have to do the homework on his personal gear.
Yes. You must ensure they offer adequate side protection. You must ensure they are maintained and not scratched to the point of obstructing vision.
And if you don't do that verification,
If a piece of shrapnel shatters his personal glasses and blinds him, OSHA will cite the employer for failing to ensure adequate hazard mitigation. The origin of the glasses doesn't matter. The fact that you allowed them on your floor does.
it all comes back to managing the system. You have to control every variable. And that ties into a really fascinating strategy from the text for managing these variables, known as prevention through design, or PTB.
Yes. Prevention through design is basically the holy grail of modern safety engineering.
How so? Define it for us.
It's the practice of anticipating hazards and engineering them out of the process, the tools, or the facility layout during the initial design phase, like long before a worker ever sets foot on the floor.
So fixing it on the blueprint.
Exactly. But sometimes you run into the immutable laws of physics and commerce.
Right. Let's look at the metal fabricating facility scenario from our sources.
Yeah.
We want to apply PTD to eliminate sharp edges. Right?
Wow.
That's the goal. But the entire purpose of a metal fabricating plant is to cut raw steel into specific shapes. You inherently create incredibly sharp, jagged metal burrs in that process. You literally cannot engineer out the sharp edge of the product you are being paid to manufacture.
In that scenario, elimination and substitution, the top of our hierarchy, are physically impossible. The raw hazard is inherent to the product itself.
So what does the hazard assessment dictate then?
It dictates a multi-layered defense. You provide cut-resistant Kevlar gloves and sleeves, that's your PPE.
Okay.
But to align with the PTD philosophy, you integrate that gear with administrative controls. You design workstations that minimize the need to blindly reach around the sharp materials.
Oh, so changing the workflow.
Yes.
Yeah.
You implement strict training protocols on material handling. The PPE isn't just a standalone, lazy solution. It becomes a single integrated component of a much broader operational design.
Which requires the safety professional to be highly perceptive. You aren't just staring at a machine and checking a box.
Not at all. You are modeling a complex biological and mechanical interaction.
You have to visualize the environment. In the ambient temperature 100 degrees, will sweat cause the workers' safety glasses to slide down their nose right when they need them?
Will the noise of an adjacent pneumatic press prevent them from hearing a forklift backup alarm while they're wearing your mandatory earmuffs?
Right. You are evaluating human factors engineering. You can possess a flawlessly calculated hazard assessment, and you can purchase the most technologically advanced, expensive gear on the global market.
But that $1 million investment is utterly worthless if the equipment does not stay securely on the worker's body.
And that reality slams us directly into the most volatile element of this entire discussion: human behavior, fit, and training.
The human element, always the hardest part to engineer.
We can calculate the tensile strength of Kevlar all day, but humans aren't mathematical constants. We are dealing with fatigue, comfort, psychology, physical variation.
And the regulations attempt to wrangle this chaos by mandating highly specific training criteria.
Right. Before an employee is allowed to touch a piece of PPE, they must be trained on 5 critical pillars.
Let's run through them. They need to know exactly when the gear is necessary.
Okay, when?
What specific gear is required.
Why?
How to properly don, doff, adjust, and wear it.
Donning and doffing. Putting it on and taking it off.
Exactly. Then the structural limitations of the equipment. And finally, the proper care, maintenance, and disposal procedures.
That sequence of donning and doffing is fascinating to me because it's so frequently overlooked, yet the sources emphasize it's a massive vector for injury and exposure.
Oh, it's huge. Imagine a worker handling a highly toxic powdered chemical. They're wearing a full protective suit and gloves. During the shift, the powder settles all over the outside of their gear.
Okay, they're covered in the toxic powder, but they're safe inside.
Right. But at the end of the shift, if they take their gloves off first with their bare hand, or if they pull a contaminated suit over their head without leaving their respirator on, they instantly expose themselves to the exact chemical they just spent 8 hours successfully avoiding.
Wow. So taking it off is just as dangerous as the work itself.
The sequence of doffing is a precise, practiced choreography designed entirely to prevent self-contamination.
And interconnected with that choreography is the absolute necessity of fit.
Well,
We keep using the word barrier, and a barrier must be continuous.
it has to seal. If a worker has a narrow face and they are issued a generic, wide-fitting respirator, that silicone edge is not going to seal against their cheekbone.
And a respirator that does not seal is, well, it's nothing more than a psychological comfort blanket, right?
That's all it is, because it forces the worker to draw contaminated ambient air through the path of least resistance.
Which is the gaps around the seal.
Exactly, rather than pulling it through the dense filtration cartridges. This is why quantitative and qualitative fit testing is a massive regulatory requirement.
Let's talk about that testing, because it's pretty interesting. We use substances like Bitrex, right? Which is incredibly bitter.
Extremely bitter. Or stannic chloride irritant smoke. If the worker can taste the bitterness or if they cough from the smoke while wearing the mask, the seal has failed.
You can't just ask them, does it feel tight?
No, the fit must be empirically proven.
Okay, then we have the maintenance and inspection rules. The mandate from OSHA is brutally clear. Defective or damaged PPE shall not be used, period.
Zero tolerance.
If a heavy leather welding glove has a tiny millimeter-wide tear in the wetting between the thumb and index finger, you don't patch it with duct tape, do you?
No, you throw it in the trash and issue a new pair immediately.
That zero-tolerance policy exists because hazards seek out vulnerabilities. A millimeter gap in a glove is a superhighway for a chemical solvent or a sharp edge.
The structural integrity of the barrier must be absolute.
But let's confront the psychological reality on the ground. Let's talk about thermal stress and physical discomfort.
This is where theory meets reality.
Right. If you mandate that a worker wears wraparound safety glasses for a 10-hour shift, and the hard plastic arms are constantly digging into the temporal bone behind their ears, generating this low-grade migraine, what is that worker going to do the moment the safety manager walks to a different sector?
They are going to relieve the pain. They will push the glasses up onto their forehead or just take them off completely.
Exactly. Or if a half-mask respirator is trapping heat and sweat against their face in a 95-degree warehouse, they will pull it down around their neck just to catch a breath of cool air.
And in that 1 second of human weakness, driven entirely by a basic physiological need for comfort, the entire hazard assessment is rendered meaningless.
So how do we solve this? I mean, how do you actually enforce compliance when the life-saving gear actively causes physical pain or severe discomfort? You can't just write people up and fire them every single day.
No, you'd have no workforce left.
Right. So how do you bridge the gap between regulatory theory and human acceptance?
You bridge that gap by recognizing that the workers are the true subject matter experts of their own physiological experience.
Okay, elaborate on that.
You cannot police your way to a robust safety culture. A purely punitive system only creates a culture of hiding. If you want genuine compliance, you must leverage user involvement during the procurement phase.
Giving them a seat at the table before you buy the gear.
It is paramount. The safety professional acts as the boundary setter. You determine the unyielding technical specifications.
So you say, we need a cut-resistant glove that meets ANSI level A4, and it must offer chemical resistance to toluene.
Exactly. But within those strict boundaries, you bring in several different models from various manufacturers and let the workforce test them on the floor.
You let them try them on?
Yes. You let the workers evaluate the tactile dexterity. You let them choose the style. If they prefer a wraparound sunglass style over a traditional goggle frame, as long as it meets your impact rating, you buy the style they prefer.
Because if they chose it, they own it.
Psychological ownership is the strongest driver of safety compliance. If the gear looks modern, if it doesn't cause fatigue, and if the worker actually had a voice in selecting it, their innate resistance just evaporates.
The gear transitions from a mandated corporate burden to a personalized professional tool.
Exactly. It changes the whole dynamic.
That is a profound insight for anyone managing a safety culture. All right, we have covered the philosophy, the hazard assessment protocols, and the human dynamics.
Now for the heavy lifting.
Now, we need to dive into the hard science, the materials, and the mathematics. We are going to execute a head-to-toe breakdown of specific equipment categories, focusing intensely on the technical criteria tested on the ASP exam.
Let's do it.
Let's begin at the apex, head protection. The hard hat is ubiquitous. Its primary function is mitigating blunt force trauma from falling, flying, or thrown objects, alongside providing a dielectric barrier against high-voltage electrical contact.
But all hard hats are not created equal. We have to look at the ANI Z89.1 classifications.
The exam will definitely expect you to differentiate between the types and classes, right?
Absolutely.
Yeah.
So let's start with types. Type I hard hats are engineered exclusively to reduce the force of impact resulting from a blow to the top of the head.
Think as a heavy wrench falling vertically from scaffolding right onto the top of a worker's head.
Right. Type 2 hard hats provide that top protection, but they also incorporate high-density foam liners to absorb lateral impacts. So, lows to the front, back, and sides of the head.
So if a worker trips and strikes their head against a steel girder as they fall laterally, a Type I hat offers minimal protection, right? They need a Type 2.
Exactly. And then we have the electrical classes.
Break those down.
Class G, or General, is proof tested to withstand 2200 volts.
Okay, 2200 for general.
Then Class E, or Electrical, is the heavy-duty variant. It's tested to withstand 20,000 volts, primarily used for utility workers.
And the last one.
Class C, Conductive. It offers zero electrical protection.
Why would you wear a hat with a zero electrical protection?
Because Class C hats often have ventilation vents cut into the top for heat dissipation, which is great for cooling, but it completely destroys their dielectric properties. Electricity would just arc right through the vents.
You also must understand the physics of how a hard hat actually works, right? Because it is not just a hard shell bouncing an object away.
No, the shell is just the first part. The critical component is actually the internal suspension system, that webbed harness that sits on the worker's skull.
How does that work during an impact?
When a 10-pound object strikes the shell, the kinetic energy is transferred into that suspension system, which stretches and elongates. This distributes the localized force of the impact over a massive surface area and significantly slows the deceleration curve.
So it acts like a shock absorber.
Exactly. If a worker removes that suspension system because, say, it messes up their hair,
Or if they wear a thick baseball cap underneath, that interferes with the webbing.
then a top impact will transfer catastrophic concentrated force directly into their cervical spine.
That leads directly into inspection. A hard hat must be routinely inspected for structural degradation, right? UV light from the sun makes the plastic brittle over time.
Right. If a hard hat has a hairline crack, or if the plastic has a chalky, faded appearance, it has lost its elasticity. It won't flex under impact, it will just shatter.
Let's move down to eye and face protection. We are mitigating high mass and high velocity impacts, chemical splashes, and optical radiation. We generally operate within 3 categories here. First, safety spectacles.
Spectacles must meet the ANSI Z87.1 standard.
What does that test actually look like?
It involves rigorous laboratory testing where steel ball bearings are fired at high velocities directly at the lenses to ensure they do not fragment into the wearer's eye.
Ouch. And they usually have side shields, right?
Yes, spectacles are typically equipped with side shields to prevent debris from entering the peripheral gaps.
Then we step up to goggles. The vital distinction, and a key point for hazard assessments, is that goggles form a complete continuous seal against the facial structure.
That seal is everything. If you are dealing with fine, airborne particulates like sawdust or splashing corrosive chemicals, safety spectacles are totally useless because the hazard will just drift or splash over the top rim.
You require the absolute seal of a goggle.
And you must ensure the goggles are chemically compatible. If you are working with strong solvents, certain plastic goggle lenses will fog, craze, or just straight up melt.
What if a worker wears prescription glasses?
Then the goggles must be specifically engineered to fit cleanly over their glasses without compromising the facial seal around the arms of the glasses. Or you must provide goggles with custom ground prescription inserts.
Okay, the third category is the face shield. But here is the trick from the study guides. A face shield is not primary eye protection.
That is a critical distinction that trips up many safety professionals on the exam. A face shield mitigates gross impact and large volume splashes to the facial tissue.
But debris can easily deflect under the chin and travel up into the eyes, right?
Exactly. A face shield must always, unconditionally, be worn over primary eye protection like spectacles or goggles. It is a secondary layer of defense, never the only layer.
Got it. Face shield equals secondary. Next, let's explore hearing protection. The physics of sound and hearing loss are fascinating. Noise-induced hearing loss doesn't happen because the eardrum ruptures, does it?
No, it happens because acoustic energy destroys the microscopic hair cells, the cilia deep inside the cochlea.
And once they are flattened by chronic exposure to high decibel noise,
they never regenerate. You just lose that frequency forever.
To prevent that, we rely on the noise reduction rating, the NRR, which calculates the sound attenuation provided by earplugs or earmuffs. We are trying to reduce the ambient decibel level to a safe permissible limit, typically below an 85 decibel time-weighted average.
But the NRR printed on the side of a box of earplugs is basically a laboratory fantasy.
Right. If a box says NRR 30, it doesn't actually reduce the noise by 30 decibels in the real world, does it?
It absolutely does not. The NRR is calculated in a highly controlled acoustic laboratory with test subjects who have the earplugs inserted perfectly by trained audiologists.
And in a chaotic industrial environment, workers rarely achieve a perfect insertion depth or seal.
Therefore, safety professionals must apply degenerating factors. OSHA often requires you to subtract 7 from the NRR and then divide the remainder by 2 to estimate the actual real-world protection.
Okay, let's do that math. So an NRR 30 earplug, you subtract 7, that's 23, divide by 2, that's 11.5.
Right. It might realistically only offer 11.5 decibels of attenuation on the shop floor.
So if your ambient noise is 105 decibels, that NRR 30 earplug is mathematically insufficient to get the worker down to a safe 85 decibel exposure. 105 minus 11.5 is still over 93 decibels.
Exactly. In that case, you would need to implement dual protection earplugs worn underneath heavy acoustic earmuffs.
And there is a hard regulatory line regarding existing medical conditions too, right? If a worker has already suffered a verified standard threshold shift.
Which means audiometric testing proves they are actively losing their hearing from year to year.
Right. If they have that shift, wearing protection becomes absolutely mandatory at lower action levels to prevent total deafness. You can't mess around with that.
Nope. The threshold drops from 90 to 85 decibels for mandatory enforcement.
Let's transition to hand and body protection. This is a massive field of material science. You are selecting protective barriers based entirely on the hazard profile. Are you choosing butyl rubber, neoprene, nitrile, Kevlar, leather, aluminized fiberglass.
The exam heavily emphasizes material compatibility and recognizing catastrophic combinations.
Let's examine two highly specific scenarios from the text. First, welding operations. When outfitting a welder, the protective clothing must be constructed from natural fibers like heavy cotton or wool or leather, right?
Yes.
Why? Because if a welder wears a high-performance, moisture-wicking synthetic shirt made of polyester or nylon and a 2,000-degree piece of slag lands on their chest, the fabric doesn't just catch fire, does it?
No, it's so much worse. Synthetic polymers will instantly melt. They turn into a boiling liquid plastic that fuses directly into the dermal and subdermal tissue.
Oh, man.
The resulting third-degree burns are horrific and require extensive skin grafting because you can't just peel the plastic off. It's part of the tissue now.
And natural fibers prevent this.
Natural fibers might char or smolder under extreme heat, but they maintain their structural integrity. They will not melt into the flesh.
Okay, our second scenario deals with electrical switching and the terrifying phenomenon of an arc flash. An arc flash is essentially an electrical explosion, right?
Yes. It occurs when a massive amount of electrical energy arcs through the air, ionizing the oxygen and creating a literal plasma wave.
How hot does that get?
The temperature at the center of an arc flash can exceed 35,000 degrees Fahrenheit.
Which is hotter than the surface of the sun.
It is. It generates a supersonic shockwave, blinding light, and catastrophic thermal energy.
To survive that, electrical workers must wear flame-resistant or FR clothing. But we don't just guess at the thickness, do we? We rely on a specific metric called the arc thermal performance value, or ATPV.
The ATPV is measured in calories per square centimeter.
A calorie, in this context, is a measure of thermal energy.
Right. To put it in perspective for the listener, exposure to just 1.2 calories per square centimeter for 1 second will cause the onset of a second-degree burn on human skin.
So if a hazard analysis determines a potential arc flash could generate 10 calories of thermal energy, the worker's FR clothing must have an ATPV rating of at least 10, right?
Preferably higher, like the 12 calcimeta 2 baseline, often required for specific switching tasks.
And the fabric acts as a thermal shield, absorbing and dissipating the plasma heat before it can transfer that 1.2 calories through to the skin.
The engineering behind that fabric is remarkable, but again, human behavior is the weak link.
How so in this case?
If a worker wears a 40 calcimeta 2 arc flash suit, but they leave the top button undone because they are hot, the plasma wave will instantly seek out that vulnerability, flow inside the suit, and the protection is negated.
Which brings us to perhaps the most mathematically rigorous and complex domain of industrial hygiene, respiratory protection.
This is a massive topic on the exam.
We are dealing with hazards that are invisible, odorless, and highly lethal. We categorize respirators into two major architectural classes, atmosphere supplying and air purifying.
Let's define them. Atmosphere supplying means you are entirely decoupled from the ambient environment. You are breathing clean, grade D breathable air provided from an external source.
Like a pressurized scuba tank in SCBA.
Exactly. Or through a long, high-pressure airline tethered to a compressor outside the hazard zone.
And air purifying respirators.
Those force the worker to breathe the ambient contaminated air, but they pull that air through a highly specific filter or chemical cartridge to scrub out the hazard before it reaches the lungs.
And we're scrubbing out 6 distinct types of airborne hazards. Correct, let's list them. Dusts, which are solid particles generated by crushing or grinding.
Mists, which are suspended liquid droplets.
Fumes, which are tricky. Fumes are solid metal particles formed by condensation during welding, not gases, right?
That's a huge distinction for the exam. Fumes are solid, not gas.
No.
Then you have vapors, which is the gaseous state of a liquid at room temperature.
Like paint thinner evaporating.
Right. And gases, which are substances that are naturally gaseous at room temperature, like carbon monoxide.
And the 6th hazard.
Oxygen deficiency.
Oh, that's a critical trap. An air purifying respirator cannot create oxygen, can it?
No, it cannot. If you enter a confined space where a displacing gas has dropped the ambient oxygen level below 19.5%, a filter mask will do absolutely nothing to save you. You will asphyxiate.
You must use an atmosphere supplying system in that case. Okay, let's get into the math. If you are sitting for the ASP, you must be able to calculate exposure limits and respirator capabilities.
You need to know this cold.
We're going to walk through a detailed real-world calculation involving 3 critical acronyms, APF, PEL, and MUC. Let's define the variables first.
APF is the assigned protection factor. It is a standardized number assigned by OSHA that represents the level of protection a specific class of respirator is expected to provide.
Give us some examples.
A half-mask elastomeric respirator has an APF of 10. A full-face respirator, because it seals over the entire face and protects the eyes, has an APF of 50.
This means a full-face respirator reduces the concentration of the hazard inside the mask to 150th of the concentration in the surrounding room.
Correct. The next variable is the PEL, the permissible exposure limit.
This is the absolute maximum legal concentration of a specific chemical or substance a worker can be exposed to over an 8-hour shift.
Exactly. And the final variable is what we're usually trying to solve for, the MUC, or maximum use concentration.
This is the absolute ceiling, right? It is the highest atmospheric concentration of a hazard where a specific respirator can still mathematically keep the worker's internal exposure below the legal PEL.
Let's run a scenario so it makes sense. Say we are conducting asbestos abatement. The PEL for asbestos is incredibly low, a 0.1 fibers per cubic centimeter of air.
0.1 fiber cc. Okay. We are equipping our worker with a full-face, air-purifying respirator.
The formula is straightforward multiplication. To find the maximum use concentration, the MUC, you multiply the respirator's assigned protection factor, the APF, by the chemical's permissible exposure limit, the PEL.
MUC equals APF times PEL.
Okay.
We know our full-face respirator has an APF of 50. We know our asbestos PEL is 0.1, so we multiply 50 times 0.1.
And that equals 5.0.
So our maximum use concentration is 5.0 fibers cc. So let's apply this to the real world. Our industrial hygienist takes air samples during the abatement. The lab results come back and show the ambient concentration of asbestos in the room is 3.0 fibers cc.
Well, since 3.0 is below our calculated maximum ceiling of 5.0, the full-face respirator is legally and mathematically adequate. It will successfully filter the air and keep the air inside the mask below the 0.1 PEL limit.
But what if the lab results come back at 8.0 fibers cc?
Then the system has failed. The ambient hazard has completely overwhelmed the mathematical capability of the APF 50 respirator.
Even with the mask functioning perfectly?
Even perfectly fitted, the concentration of asbestos bleeding through the filter system will exceed the 0.1 PEL inside the mask.
So what is the safety professional's next move? You can't just let them keep working.
You must immediately upgrade the class of respiratory protection. You abandon the full-face air-purifying respirator and move to an atmosphere supplying system. Or perhaps a powered air-purifying respirator, a PPR, that offers an APF of 1,000.
You scale the defense to meet the magnitude of the threat.
That mathematical certainty is what separates safety engineering from simple guesswork.
It's brilliant. Let's finish our head-to-toe breakdown with the extremities, legs and feet. We have the standard safety shoes steel toe or composite toe boots designed to mitigate crush injuries from heavy rolling objects, or metatarsal guards for extreme drop hazards.
Those are pretty standard, but the exam likes to test specialized gear too.
Right. I want to focus on a piece of highly engineered leg protection that frequently appears on exams. Chainsaw chaps.
Oh, chainsaw chaps are amazing.
If a lumberjack is operating a chainsaw, the chain is spinning at roughly 50 to 60 feet per second. If that saw kicks back, a heavy pair of denim jeans offers zero resistance. The teeth will shred denim and sever the femoral artery in a fraction of a second.
It's gruesome.
So how does a piece of fabric stop a motorized blade?
It doesn't stop the blade by acting as a hard, impenetrable wall like a steel shield. Chainsaw chaps, or faller's pants, operate on the principle of mechanical jamming.
Mechanical jamming, how does that work?
The chaps are filled with multiple layers of loosely woven, highly tensile Kevlar or ballistic nylon fibers. When the spinning chainsaw teeth bite into the outer layer of the chaps, they instantly rip into these internal fibers.
But they don't cut them.
No, because the fibers are incredibly strong but loosely woven. They don't cleanly cut. Instead, hundreds of long fibers are violently pulled out of the fabric and dragged directly into the drive sprocket of the chainsaw.
Wow.
Within a millisecond, this massive bird's nest of Kevlar tangles around the sprocket, completely binding the engine and physically locking the chain in place before it can reach the worker's flesh.
It effectively weaponizes the kinetic energy of the saw against itself. It's just an incredible piece of reactive engineering.
It really is.
You know, evaluating all this gear, the arc flash ATPV ratings, the chemical breakthrough times, the respiratory APFs, it feels exactly like equipping a character in a complex, high-level video game.
That's a great way to think about it.
You can't just max out your general armor stat and expect to survive. If you are walking into a stage filled with fire, heavy steel armor will just conduct heat and cook you alive. You need specific thermal resistance. If you are entering a poison swamp, you need chemical filtration.
Every hazard requires a bespoke defense. As a safety professional, you are constantly analyzing the specific elemental attack profile of the environment and tailoring a hyper-specific defense system to counter it.
But everything we have discussed so far, the hard hats, the earplugs, the respirators, this is all designed for general industry.
Right. Everyday operations.
This is for controlled, predictable, daily operations, where we know the chemicals, we know the concentrations, and we have established protocols. What happens when the predictability shatters?
The emergency response phase.
Exactly. What happens when a valve blows off a massive pressurized holding tank or a freight train carrying liquid chlorine derails and ruptures? We leave the realm of daily safety and escalate into the chaos of emergency response. This pushes us into HAZWOPER.
HAZWOPER, hazardous waste operations and emergency response.
When you enter this territory, the standard OSHA 1910 general industry PPV we just calculated is completely, terrifyingly inadequate.
The environment is what we call IDLH, immediately dangerous to life or health. To navigate this extreme risk, the EPA and OSHA established 4 rigorous levels of protection, levels A, B, C, and D.
These levels are guaranteed to be tested on the exam. We need to dissect the components, the physics, and the limitations of each, starting at the absolute pinnacle of human defense, level A.
Level A provides the highest available magnitude of respiratory, skin, and eye protection.
When do you use it?
You deploy a level A ensemble when the chemical is known or suspected to have high dermal toxicity, meaning it absorbs rapidly and lethally right through the skin, or when you are entering a confined, poorly ventilated space with a completely unidentified vapor.
I picture a level A suit as like a bright lime green or yellow spacesuit.
That's basically what it is. It is a fully encapsulating vapor protective envelope. It has to endure brutal testing under standards like NFPA 1991, which ensures the material can withstand a battery of highly corrosive chemicals for hours without permeation.
But let's look at the respiratory mechanics, because that's where it gets interesting. For breathing, the worker must use a pressure demand full-face SCBA.
Yes.
But the crucial detail is where the SCBA is located. It is worn entirely inside the encapsulating suit. Why?
Because if a chemical vapor is toxic and corrosive enough to require a level A suit to protect human skin, that same vapor will rapidly eat through the rubber breathing hoses and expose valves of an air tank.
Ah, so it protects the gear, too.
By placing the worker and the SCBA inside the sealed bubble, you protect the life support equipment from chemical degradation. The suit seals completely around the worker, the tanks, and their boots and gloves.
That level of isolation solves the chemical threat perfectly. But let's analyze the physiological and logistical nightmare of actually operating inside a level A suit.
The isolation is profound. First, acoustic communication is completely destroyed.
You can't just talk to the guy next to you.
No. You are sealed inside a thick plastic bubble, breathing loudly through a regulator. You cannot shout to your partner. You must rely on integrated, intrinsically safe, two-way radio communication systems built directly into the suit.
And if the radio fails?
If the radio fails, you are completely deaf to the outside world, relying entirely on visual hand signals.
That sounds incredibly stressful. And then we have to account for thermodynamics.
Yeah.
The suit is vapor tight. It doesn't let chemical gas in, which means it absolutely does not let body heat out.
This is the primary limiting factor of level A operations. Heat stress.
Because sweat can't evaporate, right?
Exactly. The human body cools itself through the evaporation of sweat. Inside a level A suit, humidity reaches 100% within minutes. Evaporative cooling completely ceases. The worker's core body temperature begins to climb rapidly.
How long can someone work in that?
In a warm environment, a worker carrying a 30-pound SCBA while wearing heavy double gloves can easily succumb to catastrophic heat stroke within 20 to 30 minutes.
To counter this, organizations often have to implement active cooling systems underneath the suit, right? Like vests packed with phase change ice packets or vortex cooling tubes connected to airlines just to keep the worker conscious long enough to turn a wrench and close a valve.
It's an extreme environment, and there is a massive operational paradox regarding training with these suits, too.
The training paradox. Explain that.
Well, navigating the physical and psychological stress of a level A suit requires extreme confidence. You can't panic in there, and that confidence only comes through repeated, rigorous, realistic training drills.
But these suits cost thousands of dollars, right?
Yeah.
And the materials are susceptible to microscopic damage from mechanical wear and tear.
Exactly. If you put a worker through an obstacle course training drill in a pristine suit, they might snag the knee on a piece of concrete, creating a tiny pinhole tear.
And you cannot risk putting that damaged suit back on the shelf and sending someone into a lethal chlorine cloud with it next month.
No, that's murder. Therefore, HA Met teams are forced to purchase and dedicate specific, highly expensive suits strictly for training purposes, destroying them over time while meticulously preserving untouched, pristine models for actual hot zone emergencies.
It is a massive financial and logistical burden. Let's step down the hierarchy to level B.
Level B is deployed when you still require the absolute highest level of respiratory protection. You are still in an IDLH atmosphere requiring an SCBA, but the hazard assessment dictates you need slightly less skin protection.
So the vapor isn't a dermal threat.
Right. The chemical vapor might be a severe inhalation hazard, but it won't rapidly absorb through the skin or dissolve your rubber air hoses.
So the suit geometry changes. Instead of a fully encapsulating bubble, the ensemble might be a heavy chemical-resistant splash suit with a hood.
And crucially, the SCBA is worn on the outside of the suit.
This external SCBA placement significantly increases the worker's mobility and manual dexterity, doesn't it?
It does. It also makes changing air cylinders much faster because you don't have to unzip a sealed bubble to access the tanks.
We then drop to level C.
Level C introduces a massive shift in respiratory philosophy. You only authorize level C when 3 specific conditions are met.
What are they?
The airborne substance must be positively identified, its ambient concentration must be accurately measured, and you have mathematically verified that an air purifying respirator equipped with specific chemical cartridges will reduce the hazard below the PEL.
So you shed the heavy, cumbersome SCBA tanks entirely. You rely on the filter masks we discussed earlier, combined with moderate dermal protection, like a standard Tyvek splash suit.
The worker's mobility and mission duration increased dramatically here, but only because the atmospheric risk has dropped.
And finally, we arrive at level D.
Which always feels like a trick question on the ASP exam.
Because level D isn't really HAZMAT gear at all.
It isn't. Level D is essentially your standard, safe daily work uniform. A worker wearing steel-toe boots, cotton coveralls, standard leatherwork gloves, and a hard hat is operating at level D.
There's no respiratory protection required.
None. It is designed solely for nuisance-level mitigation against non-hazardous physical contact in the cold zone of a site.
So I want to pose a scenario. A police officer or a local fire engine arrives first at the scene of a massive commercial highway pileup. A tanker truck is overturned and leaking a rapidly expanding puddle of an unknown fuming liquid.
A classic first responder nightmare.
They don't have time to conduct a formal industrial hygiene air sampling study. How do they know what level of protection they need? Does he just throw on an SCBA and guess?
Guessing an emergency response is fatal. First responders utilize a critical tool called the DOT Emergency Response Guidebook, the ERG.
Yeah, the ERG. I've seen those little orange books.
Yes. It is a rapid reference manual designed specifically for the initial phase of a transportation incident. The officer will look through binoculars at the 4-digit UN placard on the side of the leaking tanker. They cross-reference that number in the ERG.
Does it give them exact exposure limits?
No, the guidebook won't provide highly granular occupational exposure limits, but it provides immediate tactical directives. It will tell that officer whether the chemical reacts violently with water.
So they don't spray a hose on it.
Exactly. It tells them whether the initial isolation zone needs to be 100 feet or half a mile, and whether entry into the hot zone requires a fully encapsulated Level A HAZMAT team. It provides the crucial immediate tailoring for the initial response.
It scales the defense to the hazard instantly. It's so vital. We have spent this entire session exploring the physical and chemical laws of safety engineering. We want to eliminate the hazard, but if we can't, we build physical barriers to stop kinetic energy or chemical permeation.
But there is one specific category of hazard that completely shatters this traditional paradigm.
Right. It forces safety professionals to take the ANSI hierarchy of controls, turn it completely upside down, and rewrite the rules of engagement. We are moving out of the realm of physics and into the realm of biology.
Biological hazards.
Let's define them.
Biohazards are living, multiplying organisms. We're dealing with pathogenic bacteria like Legionella found in HVAC cooling towers, viruses like Ebola, or highly pathogenic avian influenza.
Fungi, like histoplasma found in bird droppings. And parasitic organisms. Think back to the very beginning of our conversation. We established that PPE is the least effective control, the absolute last resort, because we vastly prefer to engineer the hazard out of existence. Why does biology break that philosophy?
Because of the environment in which these hazards exist. Molds, microbes, and viral pathogens are ubiquitous. They are an intrinsic part of the natural world.
They're everywhere.
If you are a safety professional managing a team conducting mold remediation in a basement after a catastrophic flood, or if you are protecting healthcare workers responding to a highly infectious respiratory virus outbreak in a hospital ward, you simply cannot rely on engineering controls to achieve a zero-risk state.
You can't just install a giant fan and expect to vent all the bacteria out of the basement forever.
No. The hazard is microscopic, it's airborne, and it is actively replicating on the wet drywall as you stand there.
Precisely. Because you cannot eliminate a ubiquitous organism, and because engineering controls like negative pressure rooms offer only partial mitigation, the mathematical reliability of those higher-level controls drops significantly.
Therefore, the paradigm shifts entirely. In biological hazard scenarios, the wearing of personal protective equipment ceases to be the last resort.
It is elevated to become the primary, frontline, non-negotiable defense mechanism.
The respirator and the fluid-resistant gown become the main wall between the worker's respiratory tract and a multiplying pathogen.
And the gear itself functions differently too. When you analyze how an N95 respirator captures a viral particle, it's not just a microscopic sieve filtering out dust, is it?
No, it's much more sophisticated than that. An N95 utilizes specialized electret media polypropylene fibers that carry a permanent electrostatic charge.
Like static electricity.
Exactly. When a microscopic viral droplet passes through the mask, it isn't just blocked physically by a small hole. It is magnetically pulled and trapped against the charged fibers.
It's a completely different mechanism of defense compared to a chemical vapor cartridge.
And this perfectly illustrates why the safety profession cannot be a rigid, dogmatic checklist. It must be a fluid, highly adaptable applied science. Nature forces us to take the bottom rung of our sacred hierarchy and elevate it to the apex of our strategy.
And that depth of understanding, that ability to adapt the physics, the chemistry, and the biology to the reality of the threat is exactly what the ASP exam is designed to test.
It really is.
Let's bring this massive exploration to a close. If you've been tracking with us, I hope it is overwhelmingly clear that mastering ASP 11, Domain 2, Topic 8, Part K is not about memorizing flashcards on the difference between safety glasses and goggles.
It is about understanding the holistic architecture of risk. It requires the ability to evaluate a hazard mathematically, to calculate maximum use concentrations, to analyze the degradation curves of polymers, and above all, to navigate the unpredictable, chaotic waters of human psychology.
Because you have to ensure that the multi-million-dollar protective system you designed actually stays on the worker's body when the pipe bursts.
It is about engineering survival.
Engineering survival, I like that. But as we wrap up, I want to leave you, the listener, with the provocative thought to dissect. One that builds on the profound tension between extreme physical hazards and fragile human limitations. Let's return to the Level A Hazewell pursuit, the paradox of protection.
The paradox. It's a great concept.
When you seal a worker inside that advanced, impenetrable vapor protective envelope, you have achieved a mathematical victory. You have absolutely solved the chemical hazard. The toxic, corrosive gas cannot reach their skin.
But in the very act of solving the chemical equation, you simultaneously introduce a cascade of entirely new, potentially fatal physiological variables.
You introduce severe escalating heat stress that will eventually cause organ failure. You severely impair their visual acuity through a thick plastic visor that fogs with condensation.
You restrict their mobility and obliterate their manual dexterity by forcing them to manipulate delicate valves while wearing 3 layers of thick rubber gloves.
You isolate them auditorily, cutting them off from the ambient sounds of failing machinery or warning shouts.
Right.
So here is the question I want you to wrestle with as you study for your exam and as you walk your job sites tomorrow. As a safety professional, how do you manage the terrifying reality that the very equipment perfectly engineered to save a worker's life might be the exact instrument that induces the fatigue, blindness, or cognitive error that ultimately kills them?
How do you balance the flawless physical protection of a barrier against the immense psychological and physiological toll it extracts from the human being trapped inside it?
Mastering that delicate, unforgiving equation is the defining hallmark of a master safety professional. Keep wrestling with that balance. Good luck with your exam preparation. Stay vigilant out there, and we will see you on the next edition of QHSE Talks.